Hi everybody, welcome back to the next session from coordination compounds. Note down the heading Werner's theory of complexes. A very old theory, Okay, so we'll begin with what was asked in the previous year questions. So note down Werner's first compound. This was asked. Werner's first compound. So the question was from the Werner's compound. What is the compound? It is cobalt, NH3 4 times, OH 2 times. This is taken 3 times, the whole Br6. So this is the Werner's compound. And the question was, how many cobalt nitrogen and how many cobalt oxygen bonds are present in this particular compound? That was the question. Okay. So you should know the structure. Otherwise, you cannot answer this. So please note, central cobalt is attached to hydroxyls. Okay. And then further, this is attached to next cobalt. This is attached to next cobalt. This is also attached to cobalt. Okay, so this is OH, OH. Now, these three surrounding cobalts already attached to two hydroxyls are attached to NH3s. 1, 2, 3, 4, 5, 6. Okay, so this is the structure of the complex inside the coordination sphere. Okay, so if you can see how many cobalt oxygen bonds are there, 6 from the center, 2 from each of the periphery cobalt. So a total of 6 plus 6, 12 cobalt oxygen, and each cobalt is bound to 4 ammonias, and there are 3 cobalts like that. That is 3 into 4, that is also 12. So 12 each. 12 each. Okay. Now, what does Werner say? So he has said certain postulates. You have to know them. So according to him, according to Werner, what he said is any complex has got, the metal has got two types of valencies. One is the primary valencies and the other one is the secondary valencies. Primary valencies and secondary valency. This primary valency is otherwise called the oxidation state. Oxidation state of the metal, and secondary valency corresponds to the coordination number. It corresponds to the coordination number. So coordination number is something which gives geometry, correct? And hence secondary valencies are directional in nature. Directional meaning they are arranged in such a way that it provides some kind of geometry, while primary valencies are non-directional. So there was a question which was asked in 2019 GATE. So the question was to write the primary and secondary valencies of the complexes that were given are CO NH3 6 times Cl3. Next, CO NH3 5 times Cl2. Next, CO NH3 4 times Cl2 Cl. CO NH3 3 times Cl3. So you have to write the primary valencies and the secondary valencies. Very easy. Primary valencies corresponds to the oxidation state. So you know that ammonia is a neutral ligand, Cl is minus. Correct? So this is X plus 0 is equal to minus 3. Sorry, is equal to plus 3. If this is minus 3 means the complex will be plus 3. So here the oxidation state is plus 3. Here X plus 0 minus 1 and then you have minus 2 outside, that is equal to 0. This is also plus 3. Similarly, you can calculate the primary valencies of all the complexes which are written over here are plus 3. And what about the coordination number? I told you coordination number is the number of donor atoms. So here ammonia, 6 ammonias comprise the coordination sphere which forms an octahedral geometry and there are 6 donor atoms. Here 5 nitrogens and 1 chlorine. Here 4 nitrogens and 2 chlorines. Here 3 nitrogens, 3 chlorines. So the secondary valencies are 6 each. They are also the same. Okay, easy. Now, the next thing, what Werner said is, according to Werner, if any metal, according to Werner, let's say you have 2 ligands. So M is the metal and you have 2 ligands. Okay, let's say this is 4 in number and this is 2 in number. So any, whatever the state of the complex is, so the ligands are written in such a way that the neutral ligands come first. Neutral ligands are supposed to be written first, followed by the anionic ligands. Followed by the anionic ligand. So if you could see the examples that were written earlier, see, here only NH3 is present, so leave that. Here NH3 and chloride is given. Neutral ligand was written first. Here also, here also. So throughout what Werner said is if any complex is given to you, you have to ensure that the neutral ligands are first written, followed by the anionic ligand. Okay. So let's take a few complexes and the question. Again, another type of question that is asked is question among CO NH3. Okay, let me write it this way. Or else we'll do this properly. CO NH3 6 times Cl3. CO NH3 5 times Cl2. And CO NH 4 times Cl2 Cl. What we have to do is we have to predict the molar conductance. Predict the order of molar conductance. Okay, so how do you do that? Now we know molar conductance is directly proportional to the number of ions that are present. And we have already learned that any coordination complex which is put inside the water or whatever solution it is. So in the aqueous state, the coordination sphere will not dissociate, but the counter ions will dissociate. Correct? So if I have to take the first complex, let me label it as 1, 2, and 3. So when we put 1, 2, and 3 in water, what happens? 1 dissociates as CONH3 6 times. This is the coordination sphere, 3 plus. and 3Cl minus. What happens to the second one? CONH3 5 times Cl, and then you have this will be carrying plus 2 plus 12 Cl minus, correct? Why? Because it has only two counter ions that will be traveling as ions when you make it aqueous. And what will happen to the third one? That will be CONH3 4 times Cl2. Charge would be positive plus Cl minus. How am I understanding whether it is positive or negative? Is whether it is plus 1 or plus 2? If there are 3 minus counter ions, the charge on the sphere would be 3 plus. If there are 2 minus counter ions, the charge on the complex would be 2 plus. Okay? As a whole, it should be electrically neutral. So we can see that the maximum number of ions are present in 1. So that will have the highest molar conductance, followed by 2 and then 3. Okay? Such type of questions can come. Okay. Another question, one last question, and then we'll end this. Or two more questions. We'll do two more questions. The next question is, which of the following gives only 25 percentage moles of Cl as AgCl when treated with AgNO3? When treated with AgNO3. Try this question on your own. Options are PtCl2.4NH3. You have to write it as coordination complexes first of all. PtCl4 5NH3. PtCl4.4NH3. And last one is PtCl4.3NH3. Pause the video, try it on your own. Okay, so first of all, we have to write the way these coordination complexes would be according to Werner. So according to Werner, what he said is you have to write the neutral ligands first. So PT in the first one, 4 NH3s, so NH3 4 times. And as nothing is mentioned, we can proceed with the notion that the complexes which are formed, those are octahedral complexes. Okay, so 4 ligands in and then Cl2. This is the first complex. This is the first complex. Correct. The next one is BPT 5 NH3s. And then it is octahedral. You will have only 6 ligands surrounding the metal. So one Cl will be inside the coordination sphere. The other two would be outside. Counter ion. C. PT NH3 4 times. 2 Cl2 will be inside and 1 Cl will be outside. So this is how Werner notates any coordination compound. Sorry, this is 3. Okay. So the question is, out of these, when you add AgNO3 to the system, we know that when we add AgNO3 to the system, AgCl will be precipitated. But will the Cl which is present inside the coordination sphere precipitate? No. Why? Because it's not ionizable. Okay, so here there won't be any reaction because there are no chlorines that are outside the coordination sphere. But here, when you add AgNO3, what will happen? There are two Cl ions which are outside and they'll be precipitated as 2 AgCl. In the third case, it would be 1 Cl is outside. So upon the addition of AgNO3, 1 AgCl will be precipitated. And the last one also, 1 Cl is outside, so AgCl, 1 mole will be precipitated. The question is, out of all the Cl which is present, which will give 25% of precipitate? 25. What is 25%? 25% is 25 by 100. That is 1 out of 4. Which one is the correct answer? Option D, no doubt. There are 4 Cl in the system, out of which only 1 is being precipitated, meaning 25% is what is being precipitated. Easy. Okay? Option D is the correct answer. All right. Next question, mark it as important, was asked in gate numerical type question. Werner's theorem. Oh. The question is, a complex is composed of 1 chromium ion, very important, 3 bromide ions, and 6 water molecules. Okay. Now what it says is, upon addition of excess AgNO3, 1.09 grams of aqueous solution of complex gave 0.94 grams of AgBr. The molecular formula of the complexes. Molecular formula of the complex is. Options are CrH2O6 times Br3. Option B, CrH2O5 times Br. And then you have Br2.H2O. C, CrH2O4 times Br2, Br2H2O. D, CrH2O 3 times Br 3 times 3H2O. Very beautiful question. So also the masses are given. For chromium, it is 52. Ag, it is 108. For bromine, it is 80. Oxygen, 16. Hydrogen, 1. It is given. Okay. So they read the question. A complex is composed of 1 Cr, 3 Br minus, and 6 water molecules. Okay. So let's write the total mass of the complex first. The total mass of the complex is 1 chromium is there, whose mass is 52. Correct. 3 Br minus is there, which is 3 into 80. Plus 6 water molecules, that is 6 into 18. 6 into 18. So upon adding this, the total mass of the complex is going to be 400 atomic mass units. Now, if we have to convert atomic mass units to mass, you know that what do we do? 1 AMU is equal to 1.67 into 10 to the power minus 24 grams. We have to convert because in the questions, the units are not in atomic mass units, it is in mass. So we need to convert that. Okay. So when you convert it, what do you get? Very easy. 400 AMU in mass, you will get 400 into 1.67 into 10 to the power minus 24 grams. This is the mass of the complex. Okay. From this particular mass of the complex, it is given that when AgNO3 was added, and 1.09 grams of the complex. So this corresponds to the mass of 1 mole of complex. But it was said that when this much amount of complex was put, this much amount of AgBr was precipitated. Okay, so what is this is mass of 1 mole of complex. Are you getting my point? Now, what is mass? So the precipitate is AgBr, correct? Mass of 1 mole of AgBr. What will that be? Ag is 108, Br is 80. So that is equal to 188 AMU. Or we can say that is equal to 188 into 1.67 into 10 to the power minus 24 grams. Okay, so this is the mass of the complex and this is the mass of the precipitate corresponding to 1 mole each. 1 mole each. Now listen very carefully. When you have 400 into 1.67 into 10 to the power minus 24 grams of the complex, the amount of precipitate that we will get of AgBr is going to be 188 into 1.67 into 10 to the power minus 24 grams of AgBr. Now what we have to do, we have 1.09 grams of complex in the question. Okay, we have 1.09 grams. So we have to find how much of precipitate is formed from 1.09. It is already given that it is 0.94. We have to find the number of moles. We'll find it. Okay, so this is 1 mole of complex giving 1 mole of AgBr. So we are now normalizing it with respect to the mass which is given in the question, 1.09. Okay, so let's try to find if it was 1:1, how much would have been given? So x into 400 into 1.67 into 10 to the power minus 24 is equal to 188 into 1.67 into 10 to the power minus 24 into 1.09 grams. Now, x is equal to 188 into 1.6, that will get cancelled. 1.67 will get cancelled. Okay, so x is equal to 188 into 1.09 grams divided by 400. And you will get this as 0.47 grams. So actually, if 1 mole of AgBr, if it was produced from 1.09 gram, you would have got 0.47 grams of AgBr. If it was in the ratio of 1:1. But in the question, it is given that the amount of precipitate, given the mass of precipitate was 0.94. So 0.94 by 0.47 is 2. 2, meaning you are getting 2 moles from a single complex. Are you understanding the point? So if we took just 1 mole of the complex, you would get 1 mole of AgBr. And with the same ratio of 1:1, if you take 1 gram of the complex, we found how much of X was formed, how much of AgBr was formed, and we found that it is 0.47. But in the question, it is given that the amount which is formed is 0.94. And we found that it corresponds to 2 moles of AgBr which is formed. So 1 mole of complex is giving you 2 moles of the precipitate. So what is the correct answer? See, here you will get 3 moles because there are 3 Br, so 3 AgBr will be formed. Here there are only 2 Br, so you will get 2 AgBr as the precipitate. Option B. Here you will get only 1 AgBr. Here you won't get any precipitate. So the correct answer is option B. Very important type of question connecting basics of inorganic chemistry with that of Werner's theory. Okay? All right. So that's all for this session. You can note down the next heading, valence bond theory. See you in the next.